lecture 12, and it will be largely focused on the physics of this one class of materials, which is extremely important. It's the backbone of our IT technology, semiconductors. Also host to many fascinating physics phenomena beyond just understanding semiconductors themselves. Semiconductors are elements in new discoveries that are being made, and that will be introduced in subsequent lectures. And we are going to also touch a bit on metals and insulators to continue the discussion of the optical properties that we started last time. And so actually going to start with reminding you what we did last time in terms of understanding the optical properties of materials using the band theory, right? And we realized that the band gap is a crucial parameter and also notion in this understanding these optical properties, because when you have a situation like this for an insulator or a semiconductor, right, with one band completely full, and then the next band up, higher in energy, completely empty, you could actually absorb a photon and kick one electron up into the higher band, but a photon with a band with an energy smaller than the band gap will not be absorbed. It will just go through. And so materials with large band gaps tend to be transparent to visible light, especially materials with a band gap larger than this. And then materials with a smaller band gap absorb part of the light, and so they can have color. We saw these examples of that last time. And then materials with a very small band gap absorb the entire visible light, and that is the case for the common semiconductors that we're going to talk about today, things like silicon and gallium arsenide. So they absorb visible light. They still have a band gap, but all the light that we can see with our eyes gets absorbed, doesn't get through. So to us, they look opaque. But if we had infrared vision, we put infrared goggles, for example, they would be transparent because those infrared photons can actually go through without being absorbed, those materials. This is an absorption experiment done with this semiconductor indium antimonide. Indium antimonide has the smallest band gap of many semiconductors, actually the smallest band gap of this important family that combines group 3 and group 5 elements. So indium is in group 3 in the periodic table and antimony in group 5. So this is a material used actively in things like infrared detectors because it has a small band gap, and so it can actually absorb even some of the infrared radiation. So the band gap, you can actually see it from this plot. So this is absorption versus energy. And for energy smaller than the band gap, there is no absorption. So the band gap is something like 0.2 electron volts. It's a really, really small band gap compared to those other materials, right? We can see up to 3.2 electron volts. This is just a fraction of that indium antimonide. So as soon as you hit the band gap edge, absorption ramps up very rapidly, and you can measure this by shining light on a material and measuring what's getting through, you can measure on the other side. And that's the absorption experiment. Okay, so you can see the band gap from such a measurement. Now, what about metals? I already mentioned to you briefly, metals have the Fermi energy in the middle of the gap. And so there are states with very, very small energies available for electrons to be kicked up to. So if all the states below the Fermi level are filled, all the states above are empty, but there are states going right to the Fermi edge that are available. This is in contrast with semiconductors or insulators where you have to cross the band gap. What this means is that a photon of any energy can be absorbed in this kind of material, in a metal. So a lot of the properties of metals are explained by electromagnetism, as well as we can see in terms of reflections of the waves. So I'll have a slide on that later on. But from the band theory point of view, this is what's happening. So metals are not transparent. They are all these kind of shiny materials. So they don't transmit light through, but they can reflect. That's why they can be shiny. So we'll see that in a moment. Now, you also know that metals have different colors. A lot of the metals are silver color, silvery, but some metals are yellow or red. Like copper is more on the red, and gold is, of course, yellow, or brass, alloys like that. So that's related actually to the width of the band. So if you imagine, remember from the tight binding model, for example, the band width is 4 times J, the tight binding parameter J. So when the atoms are the orbitals of the atoms are stronger coupled, J grows and the bandwidth grows, and that can be different for different materials. And so for material like silver, it tends to be larger. So the bandwidth is larger, and all kinds of photons in this energy range get absorbed very easily in the same band. Right? You can also kick it to the next band with higher energy, but all these photons get absorbed easily. And then when the bandwidth is narrower, then you can imagine that lower energy photons get absorbed easier than the higher energy photons. And so that gives colors to metals. At least it's responsible for part of it. Now, this is metals. This bit is about insulators. So imagine you have an insulator, so material with a large band gap, and so it's transparent, something like diamond. We will see in a moment. Now, in this diamond, there could be impurities, and we will talk about impurities more today and next time. But what these impurities are is a substitution of one or a few atoms in diamond with another atom, or maybe a missing atom in a crystal lattice, some kind of an impurity. And what happens then is that there might be an eigenstate inside the gap. There might be an eigenstate due to an impurity inside the gap. So you can think about bands as being formed of eigenstates of orbitals related to each atom. Right? So, and they form a continuous band, and they sort of bunch together, and then there's a forbidden region, which is the band gap. Now, impurity is an irregularity in the band structure, and so its eigenstate may come out of the band and be at some other energy within the band gap. And you can see what that allows you to do. It allows you to jump to the impurity with a photon, occupy the impurity, and so absorb a photon into the impurity. Or if impurity is occupied, you can jump to the higher band, and you can get absorbed into the higher band from the impurity. So it makes this insulator absorb some of the light. And so it can give color to a transparent material this way. So this is a bit about metals. This is sodium, crystal of sodium, and sodium is a metal, and however, the surface of sodium is not shiny. The surface of sodium looks like this if it's been in air for any significant time anyways. For a few minutes, it's already starting to look like that. And so what this is, it is some kind of a reaction happening on the surface, where on the surface of this metal you have an insulator, an oxide. And it's an amorphous material, perhaps. It doesn't have a regular structure, and so it makes the surface matte. But when sodium has just been cut, so this is a cut, this surface looks like a mirror for a few moments, for a few minutes, for an hour. It looks like a mirror, and then it becomes opaque. So surface properties, properties of just the first few layers of atoms, influence how metal looks in the end. So it can be shiny and transparent, shiny and reflecting, or it can be matte because of oxidation. So why does it act as a mirror? That I refer you to an electromagnetics course. But basically, you have free electrons going right to the surface in a metal, and they move together with an electromagnetic wave, screening it and generating a reflected wave in the opposite direction. So this is just an electromagnetic effect. You don't need much of solid-state physics to explain it, although Drude theory does great, essentially, in explaining this. Now, this is a bit about impurities. A remarkable demonstration of impurities giving color to crystals is these famous diamonds, which are, for example, this one is extremely valuable as a Tiffany diamond, which is famous for its yellowish color. Well, this is nothing more than one nitrogen impurity per million carbon atoms in the diamond structure. So it's just not a perfectly pure diamond crystal. It has a few of these nitrogen impurities, and each of these nitrogen impurities puts a level in the band structure. So the way to think about it is, if I draw the band structure like this, I can draw it as a function of some kind of a position x, and it's this is the band gap here, and inside the band gap there might be some levels at certain positions where the impurity is, and so it gives color to the entire crystal because impurities are uniformly distributed. This one has a different color, and so this is because it has some boron in it. And so all these minerals, ruby, and so on, they are just different concentrations of impurities, essentially. So you dig something out of the ground, you classify it as ruby or something else, but it's just an impure crystal. They're beautiful. You can go to Carnegie Museum if you haven't been. There's a whole beautiful hall with all these minerals, and just think about them being just impure crystals. We can actually generate pure crystals in the lab these days. So as of about 10 or 15 years, we can take carbon, take charcoal, and put it under pressure, and it makes diamonds. So we can create diamonds by compressing carbon, essentially carbon materials, and they can be extremely pure. They can be much more pure than the natural ones. They're also much cheaper than the natural ones. And we actually use them for things. This is a brief intermezzo, which I'll talk about more in the second part of the course after your midterm. But this is an active topic of research also in our department, where people study a particular defect called a nitrogen vacancy. And so it is a defect like this, where one of the atoms in a diamond lattice structure in a particular unit cell is replaced with nitrogen, and the other lattice site is just unoccupied. It's missing. So that's called a vacancy. It's also possible that one atom is just not there. Together with the crystal structure of diamond, together these two things, nitrogen and a vacancy, in this crystal structure form an energy level structure, which is not just one impurity level, actually, but a few different levels. So this is a fairly complicated, more complicated than the cartoon I drawn you, where each impurity adds a level. This adds a manifold of levels. And in particular, two of these levels come with different spin. And those two levels are studied for a storage of quantum information. So spin up and spin down. You can control them with microwave pulses. And so this is for this research, people request diamonds with certain impurities. They're called color centers because they all give color to diamonds. So they tell, give me this yellowish diamond, and it's going to have a high concentration of these. And then they find one of them with a laser and interrogate it to study the spin states of one of these things. All right, now back to semiconductors. We need to cover some basics of semiconductors and introduce or expand on some important concepts. So back to this situation where we, for example, shine a photon on this crystal of a semiconductor, and we take one electron up to the conduction band. So what that means, by charge conservation, for example, is that there is now one electron, it's just one electron in the conduction band in this pure example, and then there is one electron missing in the valence band. There's a full band, but there's one electron missing. And so that absence of an electron is called a hole, and we're going to talk a bit about holes today. Now, first thing about holes is that a hole, if there is one hole in the band like this, it will gravitate towards the top of the valence band. It will be at the top of the valence band. Why is that? Well, you can think about it from the point of view of electrons. Electrons obey Pauli principle, and all these red states are electrons. And so they will try to take the lowest energy, and so all the electrons will fall down. So the missing one will be at the top. Right? So that's why the hole will be at the top. But now I want you to start thinking about these holes as the actual particles. So it is actually much easier to keep track of the holes than it is to keep track of all these myriads of electrons that are occupying the valence band. There's just one hole versus billions of electrons. So keep track of the hole. And that pays off in a major way. So hole becomes a particle. It is a particle that has a positive charge. How do you see that? So it's a missing electron. There should be an electron there. So a full band, we can say that's neutral because each atom has a nucleus and it donates electrons. Right? So on average, that's a neutral situation. And now there is one electron missing in this band, so that's like a positive charge. We will see that it behaves like a particle in many other ways today. That it moves like a particle under forces, it has a mass, and so on. It has charge. And however, it's not a real particle, right? It is a quasi-particle. So I already mentioned quasi-particles to you way at the beginning of the course, and we already know some of them. For example, who can tell me a quasi-particle we already studied before? So not a real particle, an object behaves like a particle. We studied actually a couple. Phonons, right? So phonons are vibrations, collective vibrations of the lattice. And so many atoms participate in that. They vibrate. However, we used particle statistics to calculate the thermodynamic properties of phonons. We gave them momentum, right? So they are particles. They're quasi-particles, and they are bosons. Actually, there is one more quasi-particle that we already studied, but I did not emphasize that point to you. So electron in the band structure is actually not a real particle. It is a quasi-particle. Why is that? It's because, remember back to the nearly free electron model, and Bloch theorem, we said that wave functions of electrons in a crystal are of this form. So they are Bloch waves. So they look like plane waves, but with this periodic function attached to them, right? So that is not a wave function for a simple particle. That is a wave function not for a plane wave, but for a Bloch wave. And so these Bloch waves are quasiparticles made of their eigenstates of electrons in a periodic potential. So they're not quite particles. They are these modified wave functions. And these electrons, as we will see in a moment, we already saw before, they can have a different mass than in outside. So they can have an effective mass that can be very different. So those are actually electrons and holes are both quasiparticles in this case. And here in this picture, there is one more quasiparticle. Who can spot it? That's the pair, that's right. So this is the electron, right? It has a negative charge. This is a hole, it has a positive charge. And they are in the same space, right? They are in different energy bands, but they're in the same physical space. So they will actually attract, and they will form a bound state. That's called an exciton. Now, excitons are taking their name from the fact that they're excited, right? So in the equilibrium situation under normal circumstances, they're not favored, but they can be excited by something like absorption of a photon. You can create an electron-hole pair, and they will be bound together by their mutual attraction. Now, who can tell me if this is a fermion or a boson? That's right. It's a boson because it's a composite of two fermions. Two fermions makes a boson. They will combined have spin 1. They will obey Bose statistics. So in our department, there is a group where they study Bose-Einstein statistics, Bose-Einstein condensation of these kind of excitonic particles. Okay, we're actually now going to talk about excitons in this class, but I just wanted to mention them to you. Okay. Here is another property that can convince you that they can be thought of as particles. So you excite this electron into the conduction band. After some time, this is not an equilibrium situation, it can re-emit a photon with the energy of the band gap and relax back into valence band. And so this electron will fall down and make the complete valence band. And so what you can think about this process as being as an annihilation of an electron and a hole. They collide and they annihilate. So this happens due to thermodynamics. And this, however, is very much similar to the annihilation of an electron and a positron. That happens in particle physics. So also accompanied by emission of light in this case. Now, this means that electron and hole are particle and antiparticle, right? In the analogy to particle physics. Now, I think this may have even come before the particle physics concepts of positron, but I'm not sure about that. So it may have come from semiconductor physics. Particle and antiparticle. Okay, so let's think about these particles as particles. And this is a recap from before. We already saw that when we have a parabolic dispersion relation, which is the case sort of around here in the center of the band structure, we have a parabolic relation, then we can think about them as free particles with maybe just a modified mass, effective mass rather than real mass. So for a free particle, you have this dispersion relation where m would be the real mass of a particle, like the electron mass. And for a particle in a band structure, for the quasiparticle, you would have this effective mass, and you can calculate it from whichever model you're using, or you can measure it in an experiment. But for example, what we did before was to take the hopping model, the tight binding model, where the parameter J, the hopping parameter, and we saw that the dispersion relation in that model close to the bottom of the band, right? It's a cosine function, but close to the bottom of the band, it can be expanded and be a quadratic function, and the prefactor in that is JA squared. And then that corresponds to the effective mass being h bar squared divided by 2JA squared. So it's in terms of the parameters of the tight binding model, effective mass depends on the hopping and on the lattice constant. Works out to be, can be quite different from the real electron mass, from the free electron mass. Now, that was a tight binding example. We know that the band, this is an approximate model, the tight binding model. The nearly free electron model is another model we could use, or we could use more precise models than that even. But what very generically occurs is that at the minimum of the band, at the extremity of the band, let's say conduction band minimum, would always have a quadratic dispersion as long as you look close enough to the minimum. So all functions, the bands looking like this, if you go into the minimum, you can expand it in this form where you have the minimum energy, minimum of the band energy, and then the next term will be a quadratic term, right? There will be no linear term because otherwise then it wouldn't be a minimum. But there will be most of the time a quadratic term. Maybe very infrequently with special design, you may have a band structure where you have maybe a fourth term as the smallest one. But most of the time you'll have a quadratic term. Now, I'll show you next week when this is not the case, but really for most of the materials we have quadratic bands. Then we can expand this potential around this K min and E min point, which will be right here. This will be a K min, K minimum at the minimum of the band. And this parameter alpha will be basically responsible for how wide the parabola we can fit into this minimum. So it doesn't reproduce the entire band structure, but around the minimum, it's this formula. And then we can introduce a definition of an effective mass which is generic to any band structure. So effective mass will be related to the second derivative of the band in K, of the dispersion relation. So you can see that if you can expand the bands like this, then the second derivative will be related to this alpha parameter. Take the derivative twice, you will see that h bar squared over me effective is twice alpha. Right? This is just twice alpha. So whatever the band shape is in K, the curvature of the band, the second order in curvature, what's it called in English? Is that just a curvature? Yeah, it's just a curvature. So it's just related to the effective mass. Now, so that's for the mass. We can also define the speed of this particle. So always remember in the back of your mind that these are actually Bloch waves that live in bands. Right? However, we can think of them as wave packets that travel. You can track the maximum of a wave packet as it travels through space. And then we can define group velocity, which will tell us how fast the wave packet is traveling through space, and that will be how fast this particle is moving. And that is related to the derivative, the first derivative of the energy band. So the gradient in K of the dispersion relation. And so in case of this one-dimensional structure, for a given K vector, the group velocity is given by K minus K minimum and divided by the effective mass. So that would be the first derivative of this expression, basically. Okay, so that's the velocity with which a particle of mass m star is moving in the conduction band. Okay, now to the valence band. Very quickly, the concept of hole as a particle comes with a bunch of minus signs. So the same ideas apply as to electrons, but many things have minus signs. But we will go through them to sort of solidify the concept of the hole one by one. So first of all, typically the valence band bends up. So the curvature of the valence band is negative. So it's a parabola that is looking down that you can fit here in this case. This is what typically happens at the top of the valence band, right? So we're talking about the maximum of this band energy. So that's typically a parabola that bends downwards. And so there's our first minus sign here in the first red bracket. This alpha comes with a minus sign. Okay, but we are not going to define the effective mass of a hole as being negative. Right? It also looks like this is something, a dispersion relation for a particle with a negative mass. We're not going to do that. We are going to define the effective mass of a hole to be positive. And so for the valence band, we're going to define the effective mass as from this expression which has the negative of the second derivative of the band structure. And so it will be a positive expression, again, 2 alpha. Here, alpha is a positive number. So the curvature of the band is negative, but we're going to take another minus sign and define mass of a hole as being a positive number. Now, why do we do that? We do it for the following reason. It's because if we think about this hole here at the top of the band, this is the position where it has the lowest energy. If we're thinking of pushing this hole away from the top of the band, pushing it to higher momentum, that costs us energy. And so that hole will have a higher energy. So the lowest energy hole is at the top. And the higher energy holes are away. So the analogy that you can make here is, imagine you putting an empty void, a balloon underwater. Right? When you put balloon underwater, it costs you work to do that, and a balloon wants to come back up. So this is the same thing. The water, being the electrons around you, wants the balloon out. It wants to minimize its energy. So it wants the hole out. And so to have the energy go up as we go, energy of the hole go up as we go down in essentially this energy axis, we need to have this minus sign here. And then this will be satisfied. So this is actually more intuitive to put this minus sign than to have the negative hole mass. It's more confusing. Okay, so holes have positive charge and positive mass. Opposite charge, but the same sign mass. There is a simple way to measure the effective mass, and that's called cyclotron resonance. What happens is you take a material where you want to know the mass of the dominant carrier, holes or electrons, and you put it in a magnetic field. Now remember, charged particles in a magnetic field follow circular trajectories, right? And this circular trajectory is under the influence of the Lorentz force. So the Lorentz force, when it's equal to the Lorentz force, does not change the velocity of the particle in magnitude, but it changes the direction. So as the particle moves this way, it gets bent and by the Lorentz force and makes these circles, the cyclotron orbits. And so you can find from this force equality the velocity with which the particles are going to move, and then you can figure out what is the cyclotron radius or the cyclotron frequency corresponds to these orbitals. And so there will be a certain cyclotron frequency, which is how fast particle travels around circles. Now, it turns out that if you shine microwaves, these frequencies tend to be in the microwave range, so very long wavelength photons. Now, if you shine essentially photons in the microwave spectrum, and if the frequency of these photons matches this cyclotron frequency, then photons can get absorbed by this material. And so when you see the absorption feature, then you know that you've hit the resonance. And then from this formula for the cyclotron frequency, so you know the frequency by the photons that you apply. And if you look at this formula, it just has the charge, the magnetic field, which is also something you control. You can even do this experiment for different fields to convince yourselves that you're measuring something reasonable. And the other parameter here is the mass. So you can get the mass from a cyclotron resonance experiment. There is a condition that, remember there is this concept of scattering time. So if the material has a very short scattering time, then carriers cannot complete the cyclotron orbit during the scattering time. And so this experiment does not work. So scattering time has to be long enough for the electrons to complete the trajectory. And so this results in this condition for the cyclotron frequency to be larger than 1 over the scattering time. Scattering time is time between some events, scattering events of electrons of the lattice or defects and so on. Okay, so this is how you can measure it.
Quick question.
Yeah.
Does that have to be a certain type of material, like a p-doped material? Or does that work for any?
This works essentially for any material as long as this condition is satisfied. It works better for semiconductors than it works for example, metals, but because of a strong reflection of the surface of the metal.
So how would you separate
also works
out from measuring the effective mass of electrons versus volts?
All right, so that's because when you shine microwave, those photons have a very small energy, so they can't really excite you if your Fermi level is in a valence band. So if you're thinking about holes, you can't really excite across the band gap. So you will stick with probably you'll get the result from the majority carrier. There are situations where you have both electrons and holes present. I'll show you an example, and perhaps in that case you'll get 2 peaks, 2 effective masses, or several effective masses. All right. Now let's talk a bit about the dynamics of these particles. So when you, again, back to this initial experiment, when you take one electron, put it in the conduction band, it has some momentum. Now it's drawn at 0, but imagine it has some small momentum. It has some small momentum h bar k. So that momentum went into the conduction band with the electron. That means that this entire valence band is now missing that much momentum. That means the momentum of the hole is minus h bar k. Momentum of the hole that occurred in this scenario is minus h bar k. So, however, the momentum of the hole, the k momentum of the hole, is minus k of the missing electron. But we are going to define a group velocity like this, and it will have this extra minus sign here, which will mean that the hole will move in the same direction as the electron in this case. So it will have a momentum minus k, but it will move in the same direction. And so that's another minus sign that we have to worry about. Okay, so taking those concepts together, we can demonstrate that these quasiparticles, electrons or holes with an effective mass, obey Newton's equation of motion. So if you have an external force, then the particle will be accelerated, so its group velocity will change in this proportion to the second Newton's law. And you just have to use the effective mass in that law, and you will find by the known force what the acceleration is going to be. And you can actually do the opposite. You can assume this, and you can derive the other things about the band structure, about effective mass being the second derivative of the band structure of the dispersion relation, and the velocity being the first derivative of the dispersion relation. You can derive those things if you assume this one. So that goes both ways. Now here are some examples of what you can measure or calculate for different semiconductors. You can see that the effective masses deviate quite a bit from the free electron mass. So M0 is the free electron mass. Semiconductor, you have either a fully occupied valence band and the empty conduction band at 0 temperature. And if you have some electrons, right, in an intrinsic semiconductor, that means you have the exact same number of holes, because you start with a situation at 0 temperature where the valence band is completely occupied and the conduction band is completely empty. So in the intrinsic one, the density of electrons and density of holes is the same. But if you have these impurities, which we are now going to call dopants, you have atoms of another kind. They can either donate electrons or create a lack of electron at the lattice site where they exist. And then the number of electrons and the number of holes may be two different numbers. Right? So that's doping. We're going to first talk about intrinsic situation, and we're going to introduce some important statistical mechanics here. So imagine that you have a semiconductor and the valence band is completely full, conduction band is completely empty, you are at 0 temperature. This actually means that the Fermi level is in the middle of the gap, exactly in the middle. Why is that? Because to add one electron, you have to cross the gap, and you also create a hole with energy at the top of the valence band, and electron at the energy of the bottom of the conduction band. So you create two particles, and one will have the energy E gap, and one will have energy 0. So the medium of the two energies will be here. So the chemical potential is in the middle of the gap for an intrinsic material. Now we remember what happens with fermions as you smear the Fermi distribution with temperature. It becomes broadened, and at high enough temperature, the tail of the Fermi distribution can reach above the conduction band. And that means that there is a probability of occupying some particles in the conduction band just by temperature. So some of the particles will have enough temperature to hop across the band gap, and obviously this is more relevant for smaller band gap semiconductors than it is for larger band gap semiconductors, right? So for example, let me jump ahead one slide. Here, this is what electron concentration does as a function of temperature in two semiconductors, in germanium and in silicon. So you can see that in germanium at about room temperature, which is here, it starts somewhere between 10 to the 13 and 10 to the 14. This is the intrinsic carrier concentration, which you obtained by thermally activating across the band gap. So it's some kind of a number proportional to this exponential. And now this is a log plot. So it goes exponentially down with temperature, and at about 200 Kelvin, it reaches 10 to the 10. Now, the band gap of germanium is 0.66. Now let's look at what happens with silicon. The band gap is larger. So here is room temperature here in this plot, and we are already at 10 to the 10 at room temperature. So we have much less intrinsic carriers in the conduction band. At room temperature, we have the same amount as for germanium at 200 Kelvin. So at sub-room temperature, the pretty chilly temperature here. Now, what can we can calculate this density by using our statistical mechanics that we already used before. So first of all, Fermi statistics. This is the Fermi multiplier, which tells you the probability of occupying a state with a certain energy E, epsilon. And in the case when this beta, remember beta is 1 over kT, beta times energy is much greater than 1, then we can forget about this 1 here, and this prefactor just becomes this exponent. Now, what is the form of this energy? That is just a dispersion relation, quadratic dispersion relation close to the bottom of the conduction band. Close to the bottom of the conduction band is just some offset energy for the energy minimum, EC, and then a parabola on top of that. Now, another thing you need to remember for this derivation is this density of states that we derived in the beginning. So this is how many eigenstates are there at each energy. And for free particles, which these are quasi-free particles, this is the square root function. And obviously, it starts, this square root starts at EC, at the bottom of the conduction band, where the parabola starts for our quasi-free particles. So this square root function with this 3/2 prefactor is the density of states. Now, what would be the concentration of electrons in the conduction band in this intrinsic semiconductor? It's the density of states, how many eigenstates per energy, times the probability of occupying states at this energy, integrated from the bottom of the conduction band all the way to infinity. So we need to take this integral. It's the integral like this, a square root function times this exponential prefactor from the Fermi distribution. And if you take this integral, which I'm not going to do here, it works out to be this expression. So this is the intrinsic density, exactly the exponential term that we've seen in the previous slide. So this exponential term that gives this kind of carrier concentration established for these two important semiconductors. Now, let's do the same thing for the valence band. In the valence band, we have some thermal concentration of holes. And so there will be some minus signs involved. In particular, in this case, the Fermi distribution, the Fermi factor for holes is 1 minus that of electrons. So holes are missing electrons. And so it's a function like this, but works out to be this kind of term after the same approximation where we neglect +1. So the difference here is that we are taking mu and subtracting E from it. Whereas the other, for electrons, we took epsilon minus mu. So we are going in a negative axis. We're going to integrate down from the valence band top down. And this allows us to do this. So the dispersion relation is this parabola that's looking down. So that's why there is a minus sign here. The density of states is the same expression, but here we have valence band top minus energy going down. So with all these minus signs, however, the expression is very, very similar for the concentration of holes, which is P, for holes for positive, N for negative electrons, P for positive holes. We integrate from the top of the valence band to minus infinity how many eigenstates we have, the density of states, times the probability of occupying them, and we get this exponential factor here with the whole mass in front. Now, what we can do is take a product of n dot p. So the density of electrons times the density of holes, product works out to be this expression in the red square. What's interesting about it is that, of course, it has the mass of electron, mass of a hole. It has the exponential factor. So this parameter grows with temperature. The higher the temperature, the larger is n times p. But what is not in this formula is the chemical potential. Chemical potential cancels out because here we have minus beta mu, and here we had minus beta mu, so it's plus beta mu. So this chemical potential is the thing that drops out. And so this has its own name. It's called the law of mass action. And if you calculate these NP values for these different semiconductors at room temperature, you can see what they are. So much higher density N times P for germanium because of the smaller gap. Something in between for gallium arsenide, and actually much smaller for gallium arsenide, and something in between for silicon. Now, if you have an intrinsic semiconductor, then Fermi level, the chemical potential is right in the middle of the gap, and that means that the density of electrons and the density of holes is exactly the same, right? To create one hole, you need to kick up one electron, and so then you can already tell from this formula what they are. It will just be exponential factor divided by 2 here. So this will be the density of electron over hole in a intrinsic system. Now, intrinsic situation is actually sometimes very difficult to achieve. You need very pure materials. So you always have to deal with some dopants, impurities that change this perfect relation between holes and electron densities. And moreover, oftentimes you want this. You want doping for your semiconductor devices, for the physics that you study. You want this. And so the way this occurs is, for example, with silicon, you can take one atom of the silicon crystal lattice out and replace it with phosphorus. Phosphorus is one row over in the periodic table. So it has one extra electron. So now in the band structure that you have one extra electron. So you had a completely filled valence band, now plus one extra electron. So that means there will be more electrons than holes in this situation. Or you can go one row of the periodic table back. Then you can create a lack of an electron. So here's how it looks, a matrix of silicon atoms. Each of them comes with 4 electrons. So each silicon has 4 little balls around it. And now if we replace one of them with phosphorus, that comes with 5. That's a group 5 element. So it comes with 5 electrons. So there's one extra electron in this matrix. And if you go to the third column of the periodic table, this boron comes with 3, and so one electron is missing. So it is as if there was one extra hole added to the band structure. Okay. So they are called acceptors and donors. So material element that gives an extra electron is a donor, so higher in periodic table. Material that gives an extra hole is an acceptor. So this is from the point of view of the periodic table. What we've been looking at is silicon. We are in this group 4, so we have 4 electrons. So all of these guys will be acceptors. and these guys will be donors. So some machines where we grow semiconductors have these sources installed there to dope the semiconductor one way or the other, towards holes or towards electrons on purpose, or this can happen beyond our will, in addition to intrinsic carrier concentration, which can be activated by temperature. Okay, so from the band structure point of view, from the quantum mechanical point of view, what donors and acceptors do is they have their eigenstates inside the gap. Right, this is the position axis once again. So this is a band gap as a function of position. That's why it doesn't look parabolic. Just plotting the distance from the minimum to the maximum of the band structure, and whatever is in between are extra eigenstates due to dopants. So n dopants tend to line up close to the conduction band edge. And so then, upon thermal activation or a little bit of microwave or light, it's very easy for these electrons to hop into the conduction band. Very easy for them to do that. And therefore, at room temperature, you may have a much higher concentration of electrons than you have of holes because of all these levels. Now, if you cool this down sufficiently enough, all these energy levels might freeze electrons in them. So, for example, what it looks like in real space is that around the phosphorus atom, there would be a deep potential well, and if you don't have enough energy to escape from that, you'll be confined to that. And so you will not have a mobile electron. You will be confined here at low temperature. And then people talk about freezing out of carriers. So there will be no free electrons in the conduction band at low temperature. They will be frozen out in their impurity sites. And so what was effectively a conductor, like a metal, becomes an insulator at low temperature. This can happen. Now for p-dopant, the situation is symmetric. Those eigenstates tend to line up close to the bottom of the gap, close to the valence band edge. And so you can excite electrons into them. Remember, they have missing electrons, right? So they come as empty levels. You can excite easily an electron into one of these levels and reduce the number of electrons in the valence band or create a hole. And this can freeze out in a symmetric fashion as well, because even though this energy axis is going down, for holes, this is costing more and more energy to go this way. So hole will want to reannihilate with this electron, and this will, which can result in freezing out of that level at low temperature. Now, what that does to the chemical potential. So for an intrinsic system, like I told you, the chemical potential, the Fermi level, is in the middle of the gap. This is the case because one band is completely full, one is completely empty. And when you excite, you create two particles. When you have all these levels here, you shift the chemical potential up because it costs you only this much energy to put the electron in the next available eigenstate. So chemical potential is how much energy it costs you to, what's the minimum energy to put the system into the next eigenstate, into the higher energy state. So that's a much lower energy, and it's up here. And so similarly for the valence band, you go to the bottom. So the chemical potential in a p-doped material is close to the valence band edge. Chemical potential in the n-doped with negative doping or doped with donors is close to the conduction band edge. And to wrap up today, here is some relation between the band gaps and the donor levels. So these are the band gaps of different materials. We already seen for silicon and germanium that it's a fraction of of an electron volt. So a bit more than electron volt for silicon, a bit less for germanium. Gallium arsenide is a bit higher band gap, and this indium antimonide that I started with, it has around 0.2. So that's the smallest of all semiconductors. Diamond is 6. So these are all electron volt scale. Now let's look at the dopant energies. So these are milli electron volts, right? So these are energies from the band edge, so for example, difference between conduction band edge and the dopant level, or the distance between an acceptor and the valence band edge, is in millivolts. So they are very, very close to the top there. So if you have an energy band gap of 1 milli-electron volt, this is a few percent of that. So this drawing is kind of even exaggerated. Those energy levels are really even closer to the band edge. Okay, so next week we will see how these physics of semiconductors and doping give rise to devices, semiconductor devices such as transistors, diodes, solar cells, and so on. So this is very important, P and N doping. But for today, this is it. I'll see you next week.